everybody, me and Demerv are just going to give you a little introduction video to friction so that we can do the first activity about friction. There's a couple things that you probably know about friction already. It's a force, and since it's a force, it's going to be a vector. It's going to have units of newtons, and hopefully at this point you've figured out that a newton is really just a shorthand way of saying a kilogram times a meter per second squared. And if you look at Newton's second law, hopefully that's pretty clear. So, there's a bunch of things that friction could possibly depend on that you might have ideas about. I'd ask maybe pause the video right now and just try to think of some of the things that maybe friction depends on. I may have accidentally signaled my camera person to pause the video at that point. Hopefully you guys paused it and came up with some ideas. One of the main things people often think that friction depends on is velocity. And how fast the object is moving will depend on how much frictional force there's going to be. And that turns out not to be true, which may not be surprising at this point, because as we've been talking about forces, velocity hasn't seemed to have an effect on anything. Like, velocity is just velocity. With forces, we're entirely talking about acceleration in terms of what the forces can teach us about and what affects the forces. So velocity is out. Another common thing might be the roughness between the two surfaces, and that's absolutely true. The roughness between the two surfaces affects the amount of friction. If you're trying to slide something across sandpaper, it's way different than trying to slide it across ice. And Demerv will give us a quick demonstration of that. Demerv slides reasonably easily across the windowsill here, but if I move him down to the carpet, yeah, not much really going on there. Much stronger frictional force on the carpet than on the windowsill. And there's a physics term for this, the roughness between the two surfaces, and it's known as the coefficient of friction. The coefficient of friction is just a measure of the roughness between the two surfaces, and we're going to have a representation of that symbolically. And this is the first of a bunch of high-quality special effects in this video. Of this Greek letter, mu. Yeah, that's awesome. So mu is just the way we'll represent how rough the two surfaces are, and it's definitely going to be one of the things that affects how much frictional force is going to exist. Now, another thing that you might think of in terms of what affects the amount of frictional force is the weight of the object. And that's close to being true, but it's not really true. The weight of the object is not a primary thing, and I'll give you a quick example. We'll go back to the windowsill, and there's a certain amount of frictional force on Demerv as I'm pushing him across. Now, if I were to lean heavily on him while I push him, I definitely increase the frictional force, but I haven't changed Demerv's weight. I haven't changed the mass, I haven't changed the weight, I haven't changed any properties of Demerv. So what ends up being the case is that the weight isn't important. What's important is the normal force between Demerv and the surface. So the stronger the force in between Demerv and the surface, the more they're pushed together, the greater the frictional force is going to be. So the last thing that you might have thought was a cause of the force of friction would be the surface area of the object as it moves across. And that turns out not to really be true, and if we think about the two things that we have said are important so far, I think we can figure that out. So the two things are the coefficient of friction and the normal force. And the coefficient of friction is the roughness of the two surfaces. What that means is, at the microscopic level, it's how jagged the two surfaces are, really how rough they are at the microscopic level. So in the second awesome effect we have in this video, I'm going to represent this just using my fingers with little sort of jaggedness. And so we have the coefficient of friction, the relative roughness, and we have the normal force, how much they're getting pushed together. And those two things will produce a catching frictional force as they try to move across each other. And so the surface area isn't really going to matter, because if you have a larger surface area, Well, we got the same roughness, but that normal force pushing them together is spread out over a much larger area. And if we have a smaller surface area, well, it's the same roughness, but now that force is being really tightened into a very small area, and the net frictional force that will occur will end up being the same. So, normal force is important. Mu, the coefficient of friction, is important, and those are the only two things. There are also two kinds of frictional force that actually exist. There's the force of static friction, which is the force of friction that will hold an object and keep it from moving. And there's the force of kinetic friction, which is the force of friction acting on an object that's already moving. So let's start with static friction. Let's start out with a formula. So the force of static friction is less than or equal to the normal force times the coefficient of friction. And this might seem strange that all of a sudden we've got this less than or equal to sign going on here, but it would be much stranger if that less than or equal sign didn't exist. Because if it didn't exist, that would mean that the force of friction would exist no matter what else was going on, which would be weird. So for example, if mu times the normal force were 16 newtons, and I push on to MERV with 2 newtons, and then the force of friction has to be 16 newtons, there's a net force onto MERV of 14 newtons going this way, and I touch him, and he starts accelerating towards me, which would be exceedingly weird. So the thing about static friction is that it will only exert enough force to keep the object in place. And that should make sense on a lot of levels, and it's also pretty similar to what normal force does. If we put a cup of coffee on a table, the normal force acting on the coffee is just enough to hold it in place. I sit on the table, the normal force is just enough to hold me in place, and eventually there's something heavy enough that if you put it on the table collapses, and that sort of breaks the limit of the table. Static friction is a much easier thing to break in most cases. You can push on to MERV a little and he won't move, you can push on him more and he won't move, but there's some limit where you push him and all of a sudden he starts to move. So that's the key thing about static friction. It's always going to act to hold an object in place. And then if you break that mu times normal force thing, if you go over it, it'll start to move, and all of a sudden we're dealing with kinetic friction. Conveniently, kinetic friction is always some flat thing. So all of a sudden we've got the same formula pretty much, but the mu is now the coefficient of kinetic friction, which is always a little bit smaller than the coefficient of static friction for any two surfaces, and there's an equal sign. So basically, the force of kinetic friction will act on an object until it comes to rest, and then static friction will be occurring again. So kinetic friction is a little bit easier to deal with. So that should actually be enough to get you started on friction. There's an activity now where you're going to try to find the coefficient of kinetic friction for a couple different surfaces and objects being pulled across them. So yeah, take a couple notes on this, but just grab the packet and you are good to go.